Testing agencies like Laser Grade in Washington State generally utilize the 115 volts motor rating as the foundation for calculations, rather than the 120 volts nominal system voltage. The electric motors are engineered to function optimally at their designated voltage, and the 115 volts motor rating signifies the voltage level at which the motor is anticipated to generate its specified power and performance. When calculating amperage with only volt amps available, or conversely, when determining volt amps with only horsepower specified, employing the 115 volts motor rating as the basis for calculations yields more precise outcomes. The correlation between amperage, volt amps, and voltage dictates this practice. Utilizing the nominal system voltage of 120 volts can potentially underestimate the true amperage and volt amps demands. Consequently, it is crucial to adopt the 115 volts motor rating as the basis for calculations to guarantee accurate results, especially during examinations such as the General Administrator test. For instance, to calculate the full load amps, or floor, of a motor, you would use the formula amps equals volt amps divided by volts. If you are given the volt amps rating of a motor and need to find the amperage, using 115 volts instead of 120 volts will give you a slightly higher amperage value, which is more accurate for the motor's actual operating conditions. This is because motors are designed to operate most efficiently at their rated voltage. Similarly, if you are given the horsepower of a motor and need to find the volt amps, you would first convert horsepower to watts, and then use the formula volt amps equals watts divided by volts. Again, using 115 volts instead of 120 volts will provide a more accurate volt amps value. The National Electrical Code, or NEC, provides guidelines for calculating motor circuit conductor ampacity and overcurrent protection. Table 430.248 and 430.250 in the NEC list the full load currents of motors. These tables are based on specific motor voltages such as 115 volts, 208 volts, 230 volts, 460 volts, and 575 volts. When using these tables, it is important to select the correct voltage that matches the motor's nameplate rating. If the motor voltage is different from the voltages listed in the tables, you may need to adjust the full load current accordingly. NEC section 430.22 covers the sizing of conductors supplying motors. The general rule is that the conductors must have an ampacity of not less than 125% of the motor's full load current. This is to account for the motor's starting current, which can be several times higher than the full load current. For example, if a motor has a full load current of 10 amps, the conductor supplying the motor must have an ampacity of at least 12.5 amps. NEC section 430.52 covers the overcurrent protection of motors. The type of overcurrent protection required depends on the type of motor and the application. In general, the overcurrent protection must be sized to protect the motor from overload in short-circuit conditions. The maximum size of the overcurrent protection is typically limited to a percentage of the motor's full load current, as specified in the NEC. For example, for a standard motor, the overcurrent protection may be limited to 250% of the motor's full load current for an inverse time circuit breaker, or 175% for a dual-element time delay fuse. When performing motor calculations, it is essential to consider other factors such as the motor service factor, temperature rating, and duty cycle. The service factor is a multiplier that indicates the motor's ability to handle occasional overloads. A motor with a service factor of 1.15, for example, can handle a 15% overload for a short period of time. The temperature rating indicates the maximum temperature at which the motor's insulation can operate without degrading. It is important to ensure that the motor's operating temperature does not exceed its temperature rating. The duty cycle refers to the motor's on-time versus off-time. Motors that operate continuously require different considerations than motors that operate intermittently. When dealing with motor control circuits, it is crucial to understand the function of different components such as starters, contactors, and overload relays. Starters are used to provide reduced voltage starting for motors, which can help to reduce the inrush current during startup. Contactors are electrically controlled switches used to switch power to the motor. Overload relays are used to protect the motor from overloads. They typically consist of a thermal or electronic sensing element that trips a contact when the motor current exceeds a certain threshold. Understanding motor nameplate information is also crucial for accurate calculations and proper motor operation. The nameplate provides critical information about the motor's characteristics, including the rated voltage, full load current, horsepower, speed, frequency, and insulation class. It is important to carefully review the nameplate information before performing any calculations or connecting the motor to a power source. In summary, when performing electrical calculations involving motors, especially in the context of exams like the General Administrator test in Washington State, always prioritize the motor's nameplate voltage rating, typically 115 volts for smaller motors, over the nominal system voltage of 120 volts. This will help ensure accurate results and prevent underestimation of the motor's actual electrical requirements. Remember to consult the NEC for specific requirements related to motor circuit conductors, overcurrent protection, and control circuits. By following these guidelines and paying close attention to detail, you can confidently perform motor calculations and ensure the safe and reliable operation of electrical systems. To further elaborate on the practical implications of using the correct voltage in motor calculations, consider the impact on conductor sizing. As mentioned earlier, NEC Section 430.22 requires that motor circuit conductors have an ampacity of at least 125% of the motor's full load current. If you underestimate the full load current by using 120 volts instead of 115 volts, you may select conductors that are too small for the application. This can lead to overheating of the conductors, voltage drop, and even fire hazards. Similarly, using the incorrect voltage can affect the selection of overcurrent protection devices. NEC Section 430.52 specifies the maximum size of overcurrent protection devices for motors. If you overestimate the full load current, you may select overcurrent protection devices that are too large, which can prevent them from properly protecting the motor from overload conditions. On the other hand, if you underestimate the full load current, you may select overcurrent protection devices that are too small, which can cause them to trip unnecessarily. In addition to conductor sizing and overcurrent protection, using the correct voltage is also important for calculating the motor's power factor. Power factor is a measure of how efficiently the motor uses electrical power. A low power factor can result in increased energy consumption and higher utility bills. The power factor of a motor depends on its design and operating conditions. However, using the correct voltage in calculations can help to ensure that the power factor is accurately determined. Furthermore, the 115 volts versus 120 volts distinction becomes even more critical when dealing with multiple motors connected to the same circuit. The cumulative effect of using an incorrect voltage for each motor can lead to significant errors in the overall circuit calculations. For example, when calculating the total load on a feeder supplying multiple motors, it is essential to accurately determine the full load current of each motor. If you underestimate the full load current of each motor by using 120 volts instead of 115 volts, the total load on the feeder may be underestimated, potentially leading to overloading of the feeder conductors. To avoid these issues, it is always best to refer to the motor's nameplate for the correct voltage rating. The nameplate provides the most accurate information about the motor's electrical characteristics. In cases where the nameplate is missing or illegible, it may be necessary to consult the motor manufacturer's specifications. It is also worth noting that the difference between 115 volts and 120 volts may seem small, but it can have a significant impact on motor performance and efficiency. Operating a motor at a voltage that is too low can cause it to overheat and reduce its lifespan. Operating a motor at a voltage that is too high can damage its insulation and lead to premature failure. Therefore, it is important to ensure that the motor is operating at its rated voltage. In the context of electrical exams, questions involving motor calculations often require a thorough understanding of the NEC and the ability to apply the correct formulas and procedures. Pay close attention to the details of the question, including the motor's voltage rating, horsepower, and service factor. Be sure to use the appropriate NEC tables and sections to determine the conductor ampacity, overcurrent protection, and other relevant parameters. It is also helpful to practice solving a variety of motor calculation problems to develop your skills and confidence. This will help you to identify common pitfalls and avoid making mistakes on the exam. In addition to the technical aspects of motor calculations, it is also important to have a good understanding of the practical considerations involved in motor installations. This includes factors such as the ambient temperature, the motor's location, and the type of load it is driving. These factors can affect the motor's performance and reliability. For example, if a motor is installed in a hot environment, it may need to be deaerated to prevent it from overheating. Similarly, if a motor is driving a heavy load, it may require a larger starter to handle the inrush current during startup. Therefore, it is important to consider all of these factors when selecting and installing motors. In conclusion, mastering motor calculations is essential for anyone working in the electrical field. By understanding the principles outlined in the NEC, paying attention to detail, and practicing regularly, you can confidently perform motor calculations and ensure the safe and reliable operation of electrical systems. Remember to always prioritize the motor's nameplate voltage rating, typically 115 volts for smaller motors, over the nominal system voltage of 120 volts to achieve accurate results. The NEC provides comprehensive guidelines for motor installations covering aspects such as conductor sizing, overcurrent protection, and control circuits. Adhering to these guidelines is crucial for ensuring the safety and reliability of electrical systems. Furthermore, understanding motor nameplate information is essential for accurate calculations and proper motor operation. The nameplate provides critical details about the motor's characteristics, including the rated voltage, full load current, horsepower, speed, frequency, and insulation class. Always refer to the motor's nameplate for the most accurate information. The difference between 115 volts and 120 volts may seem small, but it can significantly impact motor performance and efficiency. Operating a motor at the incorrect voltage can lead to overheating, reduced lifespan, or premature failure. Therefore, it is crucial to ensure that the motor is operating at its rated voltage. Electrical exams often include questions on motor calculations, requiring a thorough understanding of the NEC and the ability to apply the correct formulas and procedures. Practice solving various motor calculation problems to develop your skills and confidence. This will help you identify common pitfalls and avoid mistakes during the exam. Besides the technical aspects, consider practical factors like ambient temperature, motor location, and the type of load it's driving. These factors can influence motor performance and reliability. In hot environments, motors may need deaerating to prevent overheating. Heavy loads might require larger starters to manage inrush current during startup. Consider all these aspects when selecting and installing motors. In summary, mastering motor calculations is crucial for professionals in the electrical field. By understanding NEC principles, paying attention to detail, and practicing regularly, you can confidently perform motor calculations and ensure the safe and reliable operation of electrical systems.